Hi, Bobby.
Hi, Aniruddhan. So,
Yes.
actually, this electronic circuits, the amplifier using BJT, then
Correct.
MOSFET, all those are very nice.
Yes.
And you were also mentioning, if you want more amplification, I can cascade. One
correct.
amplifier followed the other one, and so on.
That's correct. So I think we looked at how to get the common emitter gave us negative gain.
Yeah.
Common base gave us positive gain.
Correct.
Common collector gave us
No
ability
gain.
to no gain, but ability to drive
Yes.
something.
Yes.
Right. So we can cascade. We also said common collector can act as an output stage, things like that. So and we also mentioned you can cascade many amplifiers if you want.
Yeah.
Correct. Correct.
So I was thinking, see, initially we learned about circuit analysis. We have used that in our to analyze a circuit. And then later we also learned Thevenin, Norton, etc. That also we used in this.
Correct.
See, but Thevenin, if you look, I get information from the output side.
Correct.
I know, okay, this is the internal impedance of the source.
Correct.
And this is a source I will have.
Correct.
But I have no idea from the input side how it will look like. Because if you want to cascade, I need to know how it will behave in this circuit as an input.
That is true. So in fact, what we did was we took it across some load resistance RL.
Correct.
And we created some Thevenin equivalent of that.
Yeah.
Across those two terminals.
Yeah.
Some A and B. So we did it only across a single set of terminals.
Correct.
Right? So we made this into the Thevenin equivalent.
Yeah. So from the output side is very clear.
Correct. Correct.
But let's say this has to take input from.
Oh, okay. So you're tying it to the cascade of amplifiers because now you need to worry about input and output.
Correct.
Correct. Correct.
This is not sufficient.
This is not sufficient. Correct. So we want to analyze this, let's say, an amplifier on both the input side and the output side.
Yeah.
Right? Correct. Perfect.
So I need to know the input impedance, output impedance.
Correct.
All this.
Correct. Correct. So we need some formal way of doing this.
Formal way of doing this. Correct. Is there something?
Correct. So let us look at it. Right. So maybe what we will do. So in the case of the Thevenin, no.
Yeah.
What we did was we had some voltage source, let us say.
Correct.
Or maybe even several voltage sources.
Yeah.
We pulled them all out, used superposition. The network had some resistors, sometimes even AC resistors, capacitors, inductors.
Correct.
And I think we found out the open circuit voltage.
Yeah.
And we de-energized all the sources and found out the effective impedance.
Correct.
Or resistance in the case of a DC network, right? And across two terminals, we found this out, right? So now it is basically the way I think of it, the Thevenin equivalent, no? You have completely removed you have the electrical information, right? Voltage and current and impedance and so on, but you don't know what the structure looks like inside. It's kind of an abstract form, right? It is not, there can be many networks which can have the same Thevenin equivalent.
Correct.
Right? So we need something like that.
Yeah.
So what we will do.
So basically it can be some black box.
Exactly.
From input, how it will look like.
Correct.
And output.
Output, how
what are the parameters?
Correct. So in fact, so that's what we'll do. Maybe we'll start like that, no? So we'll just draw a box. Right? And so the way we did it here, this is Thevenin equivalent is inside a box. We will not know.
That is true.
Right? Whether the real network is there or whether this is there. So we will do the same thing. We don't know what the network is, but we have input and output.
Oh.
Right?
So just two more legs in the
two more legs in the
front.
Right?
Okay.
So earlier we had it. Now we'll just make two more legs in the front.
Oh, then I'm happy if I can.
Correct.
Okay.
So the one condition that we will do is that this only has resistors, capacitors and inductors. So basically it doesn't have any sources inside.
Okay.
That will make it easier for us to analyze. Right? So passive. So I have given examples of RLC, but there may be other passive components that we will learn. But we will say passive. So there are no sources, no voltage sources, no current sources.
Okay.
Right? Okay. And basically we've pulled out 2 leads, right? So maybe on the input side we'll call it A and B,
Okay.
output side C and D,
Okay.
right? So what we will say is at the input, so we know the reason we have two wires is because voltage is always difference, no?
Yeah.
Correct? So voltage is always difference.
Correct.
So any voltage VAB has to be the difference
Yeah.
in the voltage. Across C and D also it will be some difference, right?
All analysis also we were saying some reference node. So
Correct.
it's with respect to that.
With respect to that, right? So if I connect a voltage source, one more thing we know, if I connect a voltage source, no, at across AB, if there is some current flowing, that current has to circulate back also,
That's true.
right?
Yeah.
The same current has to come back.
That is true.
Otherwise, charge will be accumulating inside
Correct,
the 2 port,
correct.
right? So we will also make that assumption.
Yeah.
We will make some assumption like that.
Yeah.
So the current is the same. The voltage across AB, the current going in is also coming out.
Yeah.
We can do the same thing at C and D, right? So now we have 1 voltage and 1 current at the input, 1 voltage and 1 current at the output,
Okay.
right? We will give some variable for that. So normally input port, this will be port 1 and this will be port 2,
Okay.
right? That makes it easy for us to give subscription.
Subscriptions. Yeah.
Correct. So we'll call this V1. We'll call this
V2.
V2.
Okay.
We'll call this current going into port 1 I1, current going into port 2 I2, something like this, right? This is the normal convention also because passive, no? So normally if you apply V2, current will go into the port.
Correct.
So it makes sense to use this, right?
So then, okay.
Correct?
Continue.
This,
Ah.
correct. So this much we can tell.
Yeah.
Now question is how do we proceed after this, right? This convention is okay, no?
Yeah. Yeah.
Huh? So direction of currents and voltages,
Yeah.
we'll take.
Yeah.
Just like if we had a resistor, no? If you apply a voltage, the normal convention is that the current will go like this,
Yes. Yes.
right? If your assumption of the voltage is wrong, the current will also change direction. Same thing will be valid for this also. Okay, very good. So I was V by R. That's the kind of relationship we
Yes.
had for a single terminal
Yeah.
device. So first of all, this is called a 2 port, right? So 2 port system, 2 port block, whatever you want to call
network,
it. 2
all
port
that.
network, right? So now actually the resistor, capacitor, inductor were all 1 port. You had 1 voltage, 1 current. So they are all 1 port networks, 2 terminal 1 port networks. Whereas here we are talking about 4 terminal 2 port networks.
Correct.
Right? Okay. Okay. So in the case of, suppose I just had 1 block there, passive, completely passive.
Yeah.
It had RLC, for example. I only have 1 port. I don't have anything else.
Yeah.
It could be a very big network, but I can abstract it using the Thevenin equivalent impedance.
Correct.
So I only have 1 across, let's say A and B. I have 1 voltage, let's say V1, and some current I1, no?
Yeah.
Coming out also. If I find out the Thevenin equivalent, I know that the relationship between V1 and I1 is, let us say, some Z Thevenin times I1.
Yeah.
Right? So if I apply some known voltage, it draws some current. If it's AC, then I know Z Thevenin. Right? It has some phase shift, it has some magnitude. Using these two, I can find out.
Correct.
Very good. So for a 1 port, it's easy. Right? So for a 1 port network, it is easy. So this is the 2 port network.
Yeah.
Right? So I'll mark it here. What happened? Okay. Yeah. This is your 2 port network.
Yeah.
For the 1 port network, it is easy.
With whatever we know, we can manage 1 port.
We can manage 1 port. Any ideas on what we can do here?
I don't know. You have marked V1, I1, V2, I2.
Correct.
Or these are the parameters I can measure.
Exactly. Actually, you're right. Because even for Thevenin,
Yeah.
what we did was we applied a V1, measured the I1.
Correct.
So you're right.
Yeah.
So here, you don't know what is there in the
So-
network. It's like a black box. No, that's what you said.
Correct.
Correct.
So we have to define things using V1, I1, V2, I2, and so on.
Correct. So that is correct. So in this case, you can do two things, no? In the case of the one port, again, it is because we know this.
Correct.
You can take this black box. You want to find out Z Thevenin,
Yeah.
right? I can take, let's say AC, no?
Yeah.
I can apply some known
Voltage.
V1. Maybe I'll call it Vin. I find out the current IN.
Yeah.
IN is what I'm measuring.
Yeah.
I can also do the opposite. We have seen this also in examples where I can take the same one port and what I can do, I can apply IN also,
Correct.
right? And find out Vin.
In fact, for dependent sources,
Exactly.
we have done this.
We have done this,
Yeah.
right? So you can actually do either of these. It will give you Z Thevenin, right?
Yes.
So either way, Vin by IN will give you Z Thevenin.
Correct.
Right? I mean, there are some conditions. It has to be linear, passive, and
yes,
so on.
yes.
But it will work. Now here, more complicated. I have V1, I1. I have V2, I2. I can apply V1 and V2
Same time.
at the same time.
Or
Measure
separate.
I1 and I2. I can apply V1 and I1, measure V2, and there are many combinations.
Possibilities.
Too many possibilities. I can also apply I1 and I2 and measure V1 and V2. Too many possibilities, no? What shall we
So
do?
we will maybe list down the possibilities.
List down the possibilities, right? So I can, so we'll create a table here.
Yeah.
Apply, measure,
Yeah.
right? So easiest thing, apply voltage, measure the current.
Yeah.
So in this case, I need to apply V1 and V2 and measure I1 and I2, right? I can, then the next simpler one is I1. I can apply I1 and I2, that is corresponding to the second one. And I can measure V1 and V2.
Yeah. So,
I can also do V1, I1, no?
yeah.
All kinds of combinations are there actually, right?
And then we will measure V2 and I2.
V2 and I2.
Correct. And vice versa.
And vice versa. I can keep doing, I can actually choose any two of these, no?
Yeah.
I can apply V1 and I2, measure I1 and V2, all of these. So it can get quite complicated actually,
Correct.
right? So you can keep going on.
But some of them may give similar information probably.
Actually, for an passive network, just like you get the same Z Thevenin, no?
Yeah.
You get the same Z Thevenin depending on how you do it.
Correct.
All of these actually are only giving you the same information.
Correct.
It is question of what you want,
Correct.
right? If
So
you are,
then-
like you said, if you are interested in the amplifier cascade,
Yeah.
you want to apply something at the input, then find out what happens at the output, take that and apply. So you may choose certain set of parameters, right? So it also matters whether, see, this is, we said Thevenin equivalent.
Yeah.
In some cases, you may want a Norton equivalent. It may be easier.
Correct.
So if you want a Norton equivalent to be applied to the next one, you may want a different set of parameters.
So depending on that, we decide.
Correct.